All right, so start of chemistry is going to look at the smallest piece of chemistry, which is the smallest piece of matter, the atom. Okay? So the atom is the smallest particle that still retains the properties of a specific material. Right? That is, an atom of iron still retains all the properties of iron. But if I split that, it's no longer iron, it's protons, neutrons, electrons, all of that kind of stuff. Okay, so an atom is the smallest part of matter that still retains all its properties. Okay, so we're going to look at, first off, how the theories of the structure of the atom were developed, because it's a good example of how the scientific method works. Okay, and we're going to learn about some kind of important people and some important experiments that led us to what we know and understand about matter. Okay, and then we're going to look at the parts of the atom and their characteristics. Okay, and that'll be what we'll get to. Maybe we'll get through all of it today. Right, and then we'll move on to naming compounds, which should also still be reviewed for you. All right, so my suggestion here would be to have this file open on your phone, okay, so that you can add to it as needed. Okay. Obviously, it doesn't look quite the same as this because this is slides. Okay, you guys have it as a Google Doc. Okay, so before chemistry was a legitimate science, okay, we still used chemical and physical properties of matter to do stuff. Okay, having technology doesn't mean you necessarily understand how it works. Okay, we can develop something that does a job or figure out something that does a job without having to understand how it does it. Okay, and in fact, lots of technology has been developed that way. Okay, so we used things like salts to cure meat, okay, long before we understood why that worked. Okay, we tanned leather, okay, things like that. We used chemical properties and chemical reactions and stuff before we really understood what was going on because they did stuff. Okay, we knew that they worked. Didn't matter how, as long as they did. Okay, kind of the same philosophy of your phone. Okay, you use your phone all the time, but very few of us understand exactly how the whole thing works. Okay, and we don't have to. We just know it does work. Okay, chemistry was a lot like that. Chemistry wasn't even around, but we were using chemistry, okay, anyway. All right, so we'll start out with the earliest idea of the atom. Okay, the earliest idea of the atom, okay, was thought up by a Greek thinker, okay, or philosopher named Democritus. Okay, if you were in ancient Greece, the best job you could get was to be a thinker. Okay, like Plato, Aristotle, and those guys. Okay, you got to sit in the Parthenon, and people like would fan you with big palm leaves and feed you grapes, and you just had to sit there and come up with cool ideas. Okay, it was just like a sweet gig, right, to have in Greece. Well, Democritus was one of these people, and one of the days he was sitting there eating grapes, he decided, you know what? I think all matter is made up of these tiny little particles that you can't see called atoms. And everybody looked at the guy who was supposed to be waving the palm fronds at him and said, you're not doing a good enough job. This guy's obviously overheated. He ain't thinking straight. That's crazy. Okay? His whole idea about the idea of the atom was laughed at the time when he came up with it. Even though we now know it to be true, okay, it was laughed at. It was thought to be ridiculous by the ancient Greeks because they thought all matter was made of 4 things. What were those 4 things? Earth, air, water, and fire. The 4 elements. Okay? They already had this idea of how matter worked. And that idea worked well. Okay? They knew that lava, for example, was some parts fire, some parts earth, and some parts water. Okay? Why did they think that? Because it was hot, came out of the earth, and flowed like water. Okay? So it must be a mixture of all 3 types. Okay? Steam. Steam was some parts water, some parts fire, and some parts air. Made perfect sense. You mix fire and water, and it turns into this stuff that goes into the air. Okay? They had these very logical kind of things that they would use to explain stuff on Earth. Okay? If you're looking at a pile of rocks, well, that was obviously all Earth. Okay? But if you were looking at some mercury, mercury was some parts Earth and some parts water because it was a liquid metal. Okay? All of these things kind of made sense to them. Okay, so when Democritus came up with this idea of the atom, they're like, tiny invisible particles? Not so much. Okay, even though he was right. Okay, people just didn't accept it because they had an existing idea that already made sense. And this is a recurring theme in science. We have this idea. It makes sense. Don't rock the boat. Okay? There's this whole idea. Don't rock the boat. We like what we got here. It might not be perfect, but it works, so don't mess with it. Okay? And unfortunately, that's something that gets in the way of good science a lot. All right. Now, was it all bad for Democritus? I mean, this idea didn't go well, but did he come up with something good? What does his name sound like? You might study it in social. Democracy! See, it wasn't all bad. He just needed to focus on the arts and not the sciences. All right, now, during the Middle Ages, chemistry kind of took off. It wasn't chemistry yet. It was this trial and error kind of thing that people did in secret, okay, called alchemy. Okay? Alchemists were these, well, they would have looked like magicians or crazy people, okay, who mixed stuff together and made potions and elixirs and stuff like that. Okay, and what they were trying to do was get rich, basically. Okay? They were trying to come up with a drink that you could drink that would make you live forever. Most of the things they came up with had the opposite effect. Okay, like here, drink this mercury. Not good. Okay, or they mixed stuff together and noticed that it would change. Okay, they take something that was maybe a solid and another thing that was a liquid, and you mix them together, and it would turn into a gas. Okay, or it would bubble and fizz, or it would do all these strange things. So what they thought they could do was they could turn one material into another material. Okay, because that's what it looked like from kind of that level, right? Not understanding, of course, that they weren't really turning one thing into another. They were causing chemical reactions to happen that would produce new materials from what they started with. Okay, so as an example, okay, if I have, let's say, this stuff, okay, potassium iodide is a clear solution. Okay, looks just like water, basically, except it's got potassium and iodine dissolved in it. Okay, and I react that with this. Okay, this would also be a clear solution. Okay, a little bit cloudy, but essentially still like a solution, something that's dissolved in water. Okay, if I mix those two things together, okay, I get two clear solutions turning into a yellow solid with a solution sitting on top. Okay, now if you were an alchemist, you look at that and go, look what I made. I made something new. I turned these things into that. Okay, but what they didn't understand was what was really going on when they mixed those things together. They didn't make anything new. They just mixed around the materials that were in it. When this reaction happens, the lead and the potassium switch places. And so you end up with this stuff. Lead iodide, which is a yellow solid, okay, that used to be used in lead-based yellow paint, okay, and this stuff. Potassium nitrate, which is a soluble thing that would just sit on top of the yellow solid. Okay? But to an alchemist, it looks like they made something new. So that led them to believe they could turn lead into gold, because they saw other things that looked like that's what they were doing. Okay? They just didn't understand what was happening at an atomic level because the idea of the atom wasn't even around yet. Okay? So everyone kind of follow why the alchemists would have thought they can do that? Okay? We know now that you can't just make lead. You can't just go lead into gold. They're two different elements. Okay? There's no way I can turn one element into another element. Okay? It's not physically or chemically possible. Okay? But I can react things together and make it look like I did that. Okay? All right. So that's what the alchemists were trying to do. Okay? Inadvertently, they did a lot of research on chemistry. Okay? They took a lot of notes and things like that, okay, that later led to a better understanding of how matter works. Okay? So they did something important. Now, these two guys are very important. Antoine Lavoisier and Roger Bacon. They came up with the scientific method. Okay? The scientific method is what turned alchemy into a legitimate science, into chemistry. Okay? Because alchemy was just trial and error. I'm going to mix these two things together today and see what happens. Okay? As opposed to, I've got this problem I'm investigating, here's my hypothesis, here's my variables, here's my observations, here's my analysis, my conclusion, and I go from here. That was Lavoisier and Bacon. They came up with that. Okay? Before that, it was just, all right, when I mix those two things together, nothing happened. Okay? Oh, but the next day I mixed these two things together and it took 2 weeks for my eyebrows to grow back. Okay? That was all alchemy was. Okay? Just doing stuff like that. There wasn't any kind of logical rhyme or reason to it. Okay? So they took alchemy and turned it into a real science. Okay? And that, of course, then paved the way for more discoveries, more communication, importantly, between scientists, okay, that led us to a better understanding of matter and how it behaves. Okay? So if I take a chunk of, let's say, like iron, and I start cutting it into smaller and smaller pieces, okay? If I could cut it incredibly small, I could get it down to the size of a single atom. Obviously, I can't really do that. We don't have any tools capable of that. Okay? But if I could continue to cut it smaller, every single one of those smaller pieces would still be iron. Agreed? Every small piece still has all the same properties of iron. It's metallic. Okay? So they were all the same melting point, same density, all of that kind of stuff. They'd just be smaller and smaller. Okay? But eventually you get down to a single atom. Now, you can't cut that any further. I mean, you can. You can split atoms. Okay? But once I split an atom, it's no longer an atom of iron. Okay? Once I make it smaller than a single atom, now I've made something else. It no longer would have the same properties as an atom of iron. Okay? And so now I'm kind of below that threshold of, okay, properties of matter. Okay? Now I'm looking at individual protons, individual neutrons, and so on. Okay? All right, so this part here that's in bold, okay, make sure you put something beside that. Okay? The atom is the smallest particle of an element that retains the properties of that element. Okay, so looking at the atom that we've got on the board here, okay, it's got 7 protons, it's got 7 electrons, okay, so this is an atom of nitrogen, okay, the smallest piece of nitrogen that still has all the properties nitrogen has. If I were to cut this smaller, I would have 2 particles that would be different, okay, one particle would have 4 protons, the other would have 3, okay, one would have 3 electrons, the other would have 4. Okay, I no longer have nitrogen. I have a thing of lithium and a thing of beryllium. Okay, I don't have nitrogen anymore. Okay, if I cut it smaller than that, it no longer retains those properties. Okay, and that's kind of what happens in a nuclear reactor. Okay, if you're splitting an atom, okay, you're changing it from whatever it was, uranium or plutonium or whatever, into other particles. Okay, and when that happens, it releases energy. Okay, so with this idea of cutting smaller and smaller, okay, could I do that with a knife? Could I cut that small? Could I split an atom? No. Your knife, even on the sharp side, is like thousands of atoms thick, okay, even on the sharp side. So you don't have to worry about splitting the atom and causing an explosion while making soup and chopping carrots, okay? That's not going to happen. Right? But okay, I'm still making each piece smaller. In a nuclear reactor, we can split the atom. Okay? Because previously to this, it was thought that atoms were not divisible. You couldn't split one. Okay? Because we had no technology to do it. Okay? It does happen on its own in nature, very slowly, but we can accelerate the process in a nuclear reactor. Okay? So in a nuclear reactor, what you have are fuel rods. Okay? These fuel rods have embedded in their surface fuel pellets. Okay? These pellets are made of the nuclear fuel, uranium or plutonium or whatever. Okay? And they're enriched, they're very concentrated. Okay? What they do is they have an emitter over here that shoots small particles, neutrons and things like that, at the fuel rods. When those neutrons hit the fuel pellets, they cause the atoms in the fuel pellets to split. Okay, now there's a reason we use uranium and plutonium for this, right? Uranium and plutonium are really, really big atoms, Okay, so if we're looking down here, uranium has 92 protons in its nucleus. Okay, has a mass of 238 grams per mole. Okay, it's big. Okay, it's really, really big. Plutonium, even bigger, 94 protons. Okay, so they're a big target. Okay, it's like, you know, trying to put a bullet through the side of a barn. You could probably do it regardless of how bad a shot you were. All right, so you're aiming at a big target. We don't aim for things like lithium because they're too small. Okay, and splitting them doesn't release a lot of energy, even if you could. Okay, so we use these really big atoms because when we hit them, they break apart, and then the pieces go off and break other ones. Okay, and so on and so on. That's how we get that nuclear reaction. Okay, all we want out of that reaction is heat. Okay, so for generating electricity, okay, we split these atoms, they release energy, water around them gets really hot, it boils, the steam turns a turbine, and you generate electricity using nuclear power by splitting the atom. Now, this process is very controlled. If we want to generate more electricity, we lower more of the rod into the path of the particles. If we want to make less, or it's getting too hot and we don't want it to melt down, then we pull more of the rod out. Okay, so less of it's getting hit. That sort of makes sense? Okay, if something goes wrong, then you get Chernobyl. Okay, or you get a meltdown. Okay, the reactor overheats and literally everything melts. Okay, that's bad, we don't want that. All right, now, how does that process work in a bomb? Want to learn how to make a bomb? Somebody? I can't tell you exactly how it works, but I know kind of how it works. And that's really all you'd ever need to know. Because you could never build one anyway. Not that I don't have confidence in your science ability, you can't get your hands on the materials. Okay, so in a nuclear bomb, what you have is, in the middle, a big lump of this nuclear material, plutonium usually. Okay? Around it is an explosive shell, essentially a shaped charge made out of TNT or C4, plastic explosive, something like that. Okay? So in a nuclear bomb, there's two separate explosions. There's a little one and a big one. Okay? The little one detonates the explosive shell. Because of its shape, all the particles from the explosion are focused inwards onto the fissionable material that is the nuclear fuel of the bomb. Okay? All those particles go in and they hit that clump of fuel and they start the atoms splitting. Okay? Now, this is one we don't want controlled. We want this one to go crazy. We want it to go out of control. So all the little pieces that get split go off and split other atoms, and they go and split other atoms, and you get a chain reaction that causes the big mushroom cloud explosion that we associate with a nuclear explosion. Okay? So there you go. That's how you build a nuclear bomb in the most basic sense ever. Okay? But it involves taking atoms and breaking them. Okay? That is, taking them from their one form and turning them into smaller particles. Okay? That's free protons and neutrons and stuff like that. Okay? They would no longer have the properties that the original fuel had. Okay. All right. Now, late 1700s, okay, is when the idea of the atom resurfaced. Okay? A guy named John Dalton was doing experiments. Okay? And his experiments were showing, okay, these same tendencies. Okay? He was just doing experiments that involved chemical reactions, kind of basic ones. Okay? But what he was finding was that matter behaved very consistently. Regardless of which matter he was using, he was finding essentially the same patterns, which meant that maybe matter wasn't made up of 4 elements. Okay? Matter may have been made up of tiny particles, like Democritus had proposed. Okay? So what he was seeing was, in a chemical reaction like the one I showed you before with the potassium iodide and the lead nitrate, he was seeing that he wasn't making new materials. He was making new mixtures or new compounds. Okay? So if we go back to a reaction, a simple one like this, let's just say okay, so on this side of the reaction, which we call the reactant side, I'm mixing hydrochloric acid and sodium hydroxide, an acid mixed with a base. Okay? When they react, my products are water and sodium chloride. I got new materials. Did I get any new elements? No. Okay, I still have the same elements on both sides. On the reactants, I had hydrogen, chlorine, sodium, oxygen, and hydrogen. And over here, same things, hydrogen, oxygen, sodium, and chlorine. I didn't make any new elements, okay? You can never have a chemical reaction that goes like this. I mix hydrogen chloride with sodium hydroxide, and I get gold and water. Where'd the gold come from? Wasn't there to start with, therefore it can't be there at the end. This is what the alchemists were trying to do, okay? But you can't do that. Gold is its own element. It has its own atoms. They're unique. Okay? I'm not going to produce those by mixing hydrogen and chlorine and sodium and oxygen and hydrogen. It's just not going to happen. A chemical reaction is simply the rearrangement of what you already have. Okay? You're never going to produce a new element by a chemical means. Okay? Everybody all right with that idea? So that's kind of what Dalton was doing, and that was really the death of alchemy at that point. Okay? Because now people couldn't do this thing anymore. Right? So, 4 points to Dalton's atomic theory. They're super important. You might want to make a note of this somewhere, because this would definitely be a quiz type question. Okay? Like, what are the 4 points of the atomic theory? Or a multiple choice question on a test, which of the following is not part of Dalton's atomic theory. Okay? So, first point of Dalton's atomic theory, he stole from Democritus. All elements are composed of tiny, indivisible, okay? That means not splittable. Okay, not invisible, indivisible. Okay, particles called atoms. Okay, and then his second point undoes the idea of the 4 elements. Okay, everybody up until this point was still a big proponent of earth, air, fire, and water. Okay. Dalton's second point says that atoms of the same element are identical. Atoms of any one element are different from those of any other element. So basically, if I have a whole bunch of oxygen gas in a tank, every oxygen atom in that tank is the same. They're all identical. Okay? But if I have a lump of iron next to that tank of oxygen, all the iron atoms are different from the oxygen atoms. All the iron atoms are identical to each other, but they're different than oxygen atoms. Okay? So basically, there's more than 4 elements. Okay? There's, well, over 100 different elements. Okay? And they each have their own unique combination of protons, neutrons, and electrons. Okay? That's what makes them the way they are. Okay. Point number 3. Atoms of different elements can combine with one another in simple whole number ratios. And that part's important. Whole number ratios to form compounds. Okay. Here's why the whole number ratio part is important. Okay. If you look at these compounds that I've written down here, everything is a whole number. Okay. There's 1 hydrogen and 1 chlorine, 1 sodium, 1 oxygen, 1 hydrogen. 2 hydrogens, still a whole number, 1 oxygen. Okay? I never write water like this. Okay? Water is 2 hydrogens and 1 oxygen, not 1 hydrogen and half an oxygen. Okay? I can't have half an oxygen atom because atoms are indivisible. Okay? A chemical reaction doesn't produce half an atom. Okay? You're not going to split the atom by mixing vinegar and baking soda together. Okay? Chemical reaction will not alter that. Okay? So I'm never going to have a fraction in a chemical formula because that would mean I have less than a whole atom. So atoms always combine in whole number ratios. Okay, and then the last point was the death blow to alchemy. Okay, it talks about this is what happens when there's a chemical reaction. You're not producing new elements. Okay, you have the same elements in different arrangements. Okay, so chemical reactions occur when atoms are separated, joined, or rearranged. Okay, so the reaction I showed you down here this is an example of a reaction where the elements are rearranged. Okay? Hydrogen was initially with chlorine, now it's with oxygen. Okay? I rearranged the atoms. I didn't change what atoms I had, I just rearranged them. Okay? An example where atoms could be joined could be something like this. That's a chemical reaction between sodium and chlorine, where the elements are joined to form a single compound. Okay. Atoms can be separated. Okay. If you arc electricity through water, it'll split into hydrogen gas and oxygen gas. So that's all that Dalton was saying. You can't turn lead into gold. But you can cause a reaction where elements rearrange with each other. And you can cause reactions where things join together. Okay? You can split things, right? But you can't turn one element into another element. Okay? It's not possible. Okay, questions there? All right, so Dalton's atomic theory, pretty important. Now, he comes up with that theory after years and years of research. Okay? People are like, okay, yeah, your research really, seems to agree with the points you've made here. We're accepting of that. That's fine. Sure, it's, now the 4 elements are gone, but, this all seems pretty logical. The next natural follow-up question is, okay, what do your tiny indivisible particles look like? And Dalton's like, I don't know. They're tiny. Can't see them. I have no idea what they look like. Oh, no, that's not good. You got to have an answer. Okay? You come up with these 4 points, you turn chemistry on its ear, and now you don't even want to tell me what your tiny particles look like? He's like, okay, they're spheres. It was a natural assumption, right? I mean, planets are spheres, moons are spheres. It was a common, naturally occurring shape. Okay? So he said, all right, atoms are tiny little spheres. And they're like, okay, as long as you had an answer. Okay? So Dalton came up with the first model of the atom, the solid sphere model, okay? Which at the time was fine, because they didn't know about protons, neutrons, or electrons yet. Okay? All he knew was that atoms could rearrange. He didn't know why. He just knew they could. Okay? And having these little balls that could do that made sense. It was easy to make models of that. Oh, this, I'll use a red ball for oxygen, and I'll use a white ball for hydrogen, and they move around. And even to this day, when we build models of things, that's what we do. We represent little atoms with a ball. Okay? We know that that's not necessarily true anymore, okay? But it's kind of the simplest idea of it. All right? So Dalton came up with the solid sphere model. Now, his idea persisted for a very long time because nobody discovered anything to prove it wrong. It fit with all the experiments that were being done. Okay? And this is how the scientific method now comes in. Okay? We accept a model or a theory until data comes along that proves it false. Okay? Up until this point, there was nothing to prove his solid sphere model false. Until J.J. Thomson came along. Now, J.J. Thomson was also a chemist, and he was doing experiments with electrochemistry. Okay? That is, chemical reactions that can produce an electric current. Same reactions we use in batteries. Okay? Your lithium-ion battery, okay? Your car battery, okay? All of that kind of stuff. That's the kind of reactions he was working with. Well, there was a problem with that. Where's the electricity coming from? Dalton's solid sphere model couldn't explain where the charged particles that produce electrical current were coming from. Because according to Dalton, all matter was made of tiny little balls. Okay? And that didn't fit. Okay? The reason it didn't fit is this. If atoms are tiny little spheres, and you get a current flowing, you should get mass moving from one side to the other. Okay? So if you had a battery, okay, and you had it hooked up to something, the wire should get heavier and bigger as the current flows through it, if the solid sphere model is true, because the matter would have to flow through the wire. Is that what happens? Not at all. Okay? What happens is electrons, tiny little particles that are almost massless, flow through the wire. Not the atoms, just the electrons. Okay? That's what goes on in electrochemistry. He needed something to explain that. Dalton's solid sphere model didn't. Okay? It didn't account for where these little charged particles were. Okay? He knew, J.J. Thomson that is, knew that some part of the atom was positive and some part of the atom was negative, and the negative part moved. Okay? So he had to come up with some adaptation to Dalton's model that could explain that. So he came up with what he called the plum pudding model. Don't ask me why he called it that. I have no idea. I guess that maybe plum pudding has pits in it or something. I don't know. Okay? But he said, in the plum pudding model, you have a solid sphere that is positive. Embedded in its surface, very loosely, are these tiny little particles that are negatively charged. Since they make electricity, I'm going to call them electrons. Okay? That's where the name electrons come from. All right, so what he said was, in a reaction, the solid sphere gets shaken, and the electrons fall off. And that's what causes the current. Now the electrons are free to move. They would be attracted to other positively charged atoms, and they would move through a wire, okay, producing a current. Okay? It made sense. It explained his experiments. Okay? So now the plum pudding model was the accepted model of the atom, no longer the solid sphere. Okay? It's an adaptation of the solid sphere, but it's different. Okay? So what we're doing here each time is we learn something new, our old model doesn't fit, so we either throw it out or we modify it to meet the new data. Everyone kind of with me there? That's how the scientific method works. Okay, this was a very short-lived model of the atom. Once they discovered electrons, then it really got the ball rolling, literally, on changing the model of the atom. Then protons were discovered, then neutrons were discovered, okay? And we needed to have different ideas of what the atom looked like. And there was quite a bit of turmoil, actually, involved in what does the atom look like? What is the atom? There were all kinds of different models of the atom for a very long time. Okay, so shortly thereafter, protons were discovered. So then it was, okay, solid sphere, but there's a positive particle and a negative particle, and it was kind of, okay. Then there was the nuclear model, which was later proved to be true, okay, where protons and neutrons are together in the nucleus and electrons orbit them, okay, and they can be flung off at high speed more easily. That better explained how electrons moved in electric current, okay, things like that. So there was a bit of turmoil for a while. Okay, Chadwick discovered protons. Okay, discovered they weren't the only large particle. That there had to also be a neutral particle to help account for the mass, okay, of all matter. Okay, so he discovered the neutron. Okay, and then, like I say, there was all this dissension, essentially, in the world of chemistry as to what does the atom look like now. So a guy named Rutherford came along, and he performed probably the most important experiment when it comes to the nature of matter. Okay? He thought that an atom had a nucleus surrounded by electrons, but that the nucleus was really, really, really tiny. Okay? So protons and neutrons were really small. So this idea of this solid mass was wrong. There was this tiny little nucleus, okay, and there would be electrons around it, orbiting it. Okay? But there's no way to prove that because atoms are tiny. Nobody could see what they look like. So what he did is he created this experiment, okay? The Rutherford gold foil experiment. So what he did is he took essentially an X-ray machine, okay? Source of alpha particles or an X-ray machine, okay? And he took a thin piece of gold foil. So imagine a piece of tin foil, but made out of gold and much thinner. Okay, it would have had like the consistency of like a Kleenex, but made out of gold. Really, really thin, only a few atoms thick, okay, this piece of gold foil. Right? He surrounded that piece of gold foil with photographic film. Okay, you know, this is kind of a generation gap thing because you guys have only ever used digital cameras in your whole life. But cameras used to have this stuff called film in them. Okay, and when that film was exposed to light, it would brighten. It would go from like a dark brown to a bright white, and it could make the pictures on from that. It was a chemical reaction, basically. So anytime it was struck by a high energy particle, like an X-ray, it would change from brown to white. Okay? So he surrounded this gold foil with photographic film. then he turned on the X-ray machine. Okay? And the X-rays shot towards the gold foil. Now, if the solid sphere model or any variation of it was true, essentially all the particles would do what when they hit the foil? Okay? No. They would hit it and bounce back. Okay? Be like, I mean, you're shooting little particles at a solid object, right? You should hit them and it should bounce back. Okay? But remember, this gold foil is only a few atoms thick. Okay? And if Rutherford is right, and the nucleus of an atom is really small, there's space between them. Alpha particles are really, really small. They'd be able to fit through the spaces between the atoms if atoms have a really, really small nucleus. Okay? So his idea, his hypothesis was when he shot this X-ray at this thing, all the light was going to go right through. Okay? All the X-rays were going to get right through this piece of gold foil because the atoms were so small. Okay? Now he was partially right. What ended up happening was, yes, a lot of the alpha particles went right through. Okay? Which is why on the other side, this area here, okay, got a lot of hits, essentially. Okay? A lot of alpha particles went there. That part of the photographic film turned color. Okay? But he also got spots in other places that he wasn't expecting to get them. Okay? And the only way that those spots would have been exposed was because some of those alpha particles hit an atom and were deflected. Okay? Their direction was changed because they hit a nucleus and were bounced off in a different direction. Okay? He got a number of those spots. So instead of saying, well, the nucleus is incredibly small, he actually said the atom's nucleus is bigger than I thought. Okay? There is a nucleus. There is a lot of empty space because a lot of the particles went through. Okay? But there is definitely a central dense nucleus to every atom. Okay? So he proved that part correct. All right? So his experiment proved the nucleus exists, or proved the nuclear model of the atom. So that's why Rutherford is important. Okay? Rutherford essentially came up with, okay, so Rutherford, and we'll say nuclear model. Okay, there's almost always a question on your unit exam about Rutherford and his gold foil experiment and how it proves the nuclear model of the atom. Okay, so does that diagram there on the right make sense? Okay, path of the particles, some of them hit the nucleus and they bounce off. Okay, this surprised Rutherford. He wasn't expecting those results. Okay? He said it was like shooting an artillery shell at a piece of paper and having it bounce back. Okay, that's how surprised he was, okay, by those results. Okay, once the nuclear model was proved, then all the argument went to, what are the electrons doing? Fine, the electrons are really small, they're moving around the nucleus, but what are they doing? Are they orbiting like planets around the sun? Do they move randomly? Are they all evenly staggered? Okay, that no one really knew what the electrons were doing or what they looked like, because not only are atoms incredibly small, electrons are orders of magnitude smaller than that. Okay, so it was hard to kind of prove what they were doing except through indirect experimentation. Okay, so Rutherford thought the atom looked like this one on the left here. Okay, he thought all the electrons were the same distance from the nucleus, just offset. Okay? The bigger the atom, the more electrons it would have, the smaller they would be offset. Okay? Or the less the amount they'd be offset. All right? Problem with this model is that you kind of start running out of space once an atom gets to a certain size. Okay? It doesn't really work all that well. It also doesn't explain some of the things we see happen with things like photosynthesis and stuff. It doesn't really explain that. Okay? So his model didn't last very long, other than the idea that there was a nucleus. Okay? Now, Niels Bohr, okay, he did some experiments that showed that electrons sit at different energy levels. Some are close to the nucleus and would have very little energy. Some are farther away and would have much more energy. The reasons the ones that are farther away have more energy is because they can fall back towards the nucleus and release their energy. They're also moving faster. Okay? So if something's moving really fast and is really far away, it can fall a long way, it's got lots and lots of energy. Okay, so that's what Bohr said. He said, well, I don't really know exactly what that looks like. He said, but I think it probably looks like planets orbiting the sun. Okay, so you got your inner planets and you got your outer planets, and that's kind of how the electrons work. They're going to be in these nice circles, and they're going to kind of hang out in these circles at the right distance because they repel each other because they're all negative. Okay, that was his idea. And to an extent, we still accept this. Okay, if you took a picture of an atom and everything stopped, it would look like this. Okay, there'd be a certain number of electrons at the lowest level, a certain number of electrons at the next level. It'd be frozen in time, and it would look like that. But the atom's always moving, it's always changing, so it doesn't actually always look like this. Electrons can actually jump. Okay? They can jump from one level to another if they gain energy. They can also fall back to a lower level if they lose energy. Okay? And his model doesn't really explain that. Okay? It says they're fixed and they're stuck here. Okay? But in actual fact, they can jump around. Okay? They can move from one level to the next in what we call a quantum leap. Okay? They can make a quantum leap from one level to the next. Okay, now, that idea, the idea of the quantum leap, is what led to our current model of the atom. Okay? And that is de Broglie's electron cloud model. Okay? So de Broglie's model says, yes, electrons orbit the nucleus, but not in perfect circles. Okay? They're constantly moving in all kinds of patterns. They may stay at certain levels based on their energy, but when their energy changes, they'll move to a different level, different shape of orbit, and so on. Okay? So if you took a picture of an atom, okay, from far away, it would kind of look like this. You'd see electrons, a lot of them near the nucleus, and fewer further away, because ones that are further away have more energy. So it's more common to be in the lower places. All right, so in de Broglie's model, electrons can jump from one level to another. Okay, and that's how something that's a glow-in-the-dark material will work. Okay, if you guys have seen that, like you take it outside, you put it in the sun for a while, and then you put it in the dark, and it glows for a short period of time. Okay, that's because the electrons get excited when they're in the sunshine. Okay, they get excited, they gain energy, and they hop up to these higher levels. When you take them out of the sun, they start losing that energy and they start falling back down to lower levels. While they're falling, they release light energy. Okay? So they don't glow forever. They glow until they've all fallen back down to the lower levels. Okay? It's also how photosynthesis works. Okay? Plants, they're chlorophyll molecules. Okay? Same idea. In the sunshine, the electrons that are part of chlorophyll get excited, they gain energy, and they leap to higher energy levels. And then, when the sunshine is gone, they start falling back down. And when they fall back down, that energy is harnessed to make sugar. And that's how photosynthesis works. Right? So it's using the idea that electrons can change their energy and move from level to level. All right, so that's de Broglie. Okay? De Broglie's electron cloud model is our currently accepted model. Okay, so according to all of this, what we know is the atom has a nucleus. Electrons surround it. There's a lot of empty space in an atom. Okay? The electrons are always moving, but there's a fair amount of empty space in there. Okay? This is kind of where some of those orbits, or what we call orbitals, are. Okay? Because an electron can always be moving, there's not really an orbit like a planet would be in. Okay? There's an orbital. That's an area where you would be likely to find an electron based on its energy, and they are not circular. Okay? Well, one of them is. Okay, but they have really odd shapes, okay, based on their energy. All right, so last thing here to do with nature of the atom, okay, and physical properties. So all atoms have different amounts of protons and neutrons and electrons. Okay? It is the number of protons in an atom that we'll talk about tomorrow. Okay, have a good first day there, guys.